Kiel, Germany, November 1944. The naval port burned under a pale orange sky. Smoke drifted over the water, thick with oil and salt. On the pier, a team of Kriegsmarine engineers picked their way through wreckage, twisted cranes, splintered docks, and the jagged hull of a ship torn apart below the waterline. There was no crater, no impact point, just devastation that seemed to come from underneath. Commander Weiss knelt beside a fragment of metal the divers had recovered from the seabed. It was smooth, gray, and faintly magnetic. A circular fuse was fused into its skin, unmarked, unburned. He held a compass toward it. The needle spun wildly. It never touched the target, one engineer muttered, but it knew when it was close. For the first time, they realized what they were facing. A bomb that could feel metal, a weapon that waited, invisible, silent, and triggered not by pressure or heat, but by the Earth's own magnetic field. Above the harbor, the last siren faded into the wind. Germany's engineers had just witnessed the birth of a new kind of warfare, a war fought by unseen forces. In the early years of World War II, victory often depended not on courage or firepower, but on invention. Every nation raced to find a new way to outthink its enemy, a weapon that could kill more efficiently, strike farther, or survive longer. But among these thousands of experiments, one stood apart. It did not explode on impact. It did not even have to hit its target. It could sense it. The idea began not in America, but in Europe, and it started with a mine. In late 1939, as Britain struggled to contain the German Blitz across the North Sea, strange reports began to surface. Merchant ships were sinking in shallow waters near the Thames estuary and the Firth of Forth, areas believed to be safe from conventional mines. Divers who inspected the wrecks found no evidence of contact explosions. The ships had simply torn themselves apart, as if detonated from below by invisible hands. Then, in November 1939, British bomb disposal units recovered something unprecedented: an intact German mine, dragged from the mud near Shoebury-Ness. It contained no contact horns, no pressure triggers. Inside was a small coil of wire, a battery, and a magnetic sensor that could detect the hull of a passing ship by the subtle distortion it made in Earth's magnetic field. The discovery stunned British scientists. For the first time, they realized the Germans had weaponized magnetism itself. The response was immediate. Within weeks, the British Admiralty began developing degaussing, a process that wrapped ships with electric cables to neutralize their magnetic signatures. What had once been an invisible vulnerability was now a measurable field to be countered. The magnetic mine, once the terror of the seas, became a puzzle to solve. And in that race to neutralize it, another revolution began, one that would soon reach the laboratories of the United States. When America entered the war in December 1941, the lessons of Britain's early battles became blueprints for survival. The U.S. Navy quickly adopted degaussing and magnetic detection systems, but where Britain sought to defend, America sought to weaponize. If magnetism could destroy ships, it could also guide bombs, detect submarines, and trigger explosions without direct contact. In early 1942, the Office of Scientific Research and Development, the same agency that would later oversee the Manhattan Project, formed a small task force dedicated to what it called influence ordnance. The CODI term covered a new generation of weapons that used invisible forces, sound, pressure, and magnetism to determine when and where to explode. At its center was a brilliant and secretive collaboration between naval scientists and industrial engineers. The goal was simple: to build bombs and mines that could know when they were near metal and detonate only when it mattered. The first prototypes were crude but revolutionary. Tests off the coast of Florida in mid-1942 revealed how magnetic fuses could detect a ship's hull even from meters below. When the steel mass passed overhead, its magnetic influence changed the field around the fuse, triggering instant detonation. Unlike contact mines, which needed to hit their targets, these new weapons could strike without touch. For submarines, it meant death without warning. By 1943, the program had expanded into two branches. The Navy refined underwater magnetic mines and torpedo fuses. The U.S. Army Air Forces explored aerial magnetic bombs, munitions that could sense buried metal, pierce reinforced targets, and destroy from within. What linked both was the same principle: using the invisible fabric of the Earth itself as a trigger. In theory, these devices did not just react, they perceived. They knew the presence of metal the way a compass knows north. And when scaled into weapons, that awareness made them terrifyingly efficient. Germany had started the magnetic war, but by 1943 America was rewriting it. The United States was no longer imitating German technology. It was evolving beyond it, creating a family of weapons that defied the old physics of impact and blast. And soon, the same magnetic fields that guided sailors for centuries would guide bombs into the heart of Germany's most fortified cities. By 1943, the invisible war had moved from theory to production. Across the United States, laboratories once dedicated to peacetime science had become secret workshops for magnetic death. At Harvard, Caltech, and the Naval Ordnance Laboratory in Maryland, physicists and electrical engineers studied how the Earth's magnetic field could be turned into a weapon. They weren't building explosives, they were building senses. Inside each prototype bomb was a tiny coil of copper wire wound around a steel core, a magnetic induction sensor. When any large metal mass, like a ship's hull, a tank, or a bridge, passed near it, the magnetic lines of force would shift. That microscopic tremor of magnetism became a signal, feeding into a relay that detonated the charge. For the first time in history, explosives could feel their target. It was a new language of warfare. Invisible, mathematical, absolute. American scientists called them influence fuses. Each fuse could detect not only proximity, but motion. A stationary target wouldn't trigger it, only the magnetic distortion of moving steel. That made them ideal for use against ships, armored convoys, and aircraft. Even a missed bomb could still kill. If it fell close enough to a metallic structure, the field disturbance alone could set it off. To refine these systems, the U.S. Navy partnered with industry. General Electric and Westinghouse developed miniature amplifiers capable of reading minute magnetic variations. DuPont created heat-resistant casings that could survive the violent drop from bombers. And the Caltech Division of War Research worked on the timing mechanisms, ensuring detonation occurred at the exact moment magnetic signature peaked. By late 1943, the results were extraordinary. Tests in Chesapeake Bay showed that magnetic depth bombs could destroy submarines without ever making contact. One device, dropped from a Catalina patrol aircraft, exploded 20 feet above a submerged steel target, perfectly calibrated by its magnetic fuse. Observers noted the water rose like a tower, and the pressure wave below would have crushed any submarine hull within range. It was, as one report described, destruction by field, not by touch. While the Navy perfected the underwater versions, the Army Air Forces focused on something even bolder: aerial magnetic bombs. In the vast deserts of New Mexico, engineers tested fuses that could detect the magnetic footprint of buried bunkers and steel-reinforced factories. When the bomb sensed a sudden increase in metallic density below, it would trigger, often before impact. The effect was devastating. Shock waves propagated through the structure's steel skeleton, collapsing it from within. It was here that magnetism stopped being a defensive concept and became an offensive one. The Earth's field, constant, global, and measurable, had become the world's largest battlefield sensor. The enemy could hide, but not escape detection. Germany, meanwhile, had grown complacent. Having pioneered magnetic mines in 1939, the Reich had assumed it held the advantage. But by 1943, Allied scientists had quietly surpassed their innovation. German engineers continued to refine traditional contact weapons, while America turned entire coastlines into invisible minefields, activated not by pressure, but by presence. When the first shipments of American magnetic bombs reached Europe, few outside the ordnance divisions understood what they were. They looked ordinary, streamlined, compact, with a smooth casing and almost no external fuse. But inside, they carried what one Navy scientist called a listening ear for metal. Their debut came in late 1944 during the Allied bombing of U-boat pens at Brest and Kiel. Observers reported strange detonations, explosions that occurred mid-air or underwater, far from direct impact. Concrete walls cracked, docks erupted, and U-boats were ripped from their moorings. To German defenders, it looked as though the bombs had supernatural accuracy. In truth, the physics were simple: magnetic fields, amplified and harnessed by human hands. By the winter of 1944, German engineers began collecting fragments from unexploded ordnance. Inside, they found coils, vacuum tubes, and sealed chambers, electrical circuits unlike anything they'd seen before. Reports sent to Berlin called the devices magnetisch empfindliche Zünder, magnetically sensitive detonators, and their conclusion was both correct and terrifying. America had built bombs that did not need to see or touch their targets to kill them. The old war of steel and impact was ending. A new one, of science and sensation, had begun. The magnetic bomb was not just a weapon. It was a philosophy of design. Traditional bombs relied on mechanics, levers, pistons, and impact triggers that dated back to World War I. They functioned like machines. But the magnetic fuse was not mechanical. It was electronic. Inside each was a circuit that could interpret the world around it, sense changes, and react. It represented a subtle but historic shift: weapons that could think. In 1943, America's Naval Ordnance Laboratory became the silent nerve center of this leap. Its engineers borrowed techniques from radio, acoustics, and radar, fields that had little to do with explosives, and merged them into a new discipline: electromagnetic warfare. Here, magnetism was not only a property of metal, it was a language to be read and exploited. One device, the Mk6 magnetic influence fuse, became the model of this new intelligence. It used a sensitive induction coil calibrated to detect distortions in Earth's field within a range of just a few milligauss. To the human eye, that change was invisible, but to the fuse, it was the signal of a ship's death. This fusion of physics and destruction marked the dawn of something profound: the merging of scientific precision with the chaos of war. For the first time, a bomb did not depend on where it fell, but on what it sensed. Before magnetic ordnance, naval mines had to be placed carefully, often in narrow channels or at specific depths. They relied on contact or pressure, both unreliable in rough seas. But magnetic mines could wait anywhere, patient and undetectable, their sensors tuned to the subtle magnetic footprint of a vessel. When that field changed, even slightly, they would trigger. For the U.S. Navy, this meant a revolution in sea control. Entire harbors could be sealed off without physical barriers. Enemy convoys could be disrupted by invisible minefields that no minesweeper could safely detect. During the Allied advance through the Pacific, these mines crippled Japanese logistics, sinking or disabling dozens of supply ships without a single American plane or submarine needing to attack directly. The effect was psychological as much as physical. To Japanese sailors, the sea itself became hostile, a magnetic trap they could neither predict nor neutralize. No explosion was more terrifying than the one that came without warning. The brilliance of these weapons lay not only in science, but in the minds behind them. Many of the engineers working on magnetic fuses were university researchers who had never worn a uniform. Men like Dr. Merle Tuve at the Carnegie Institution, who had studied cosmic rays before the war, now applied his knowledge of magnetism to ordnance design. He once said, "Every time a bomb works properly, it means a soldier lives." They were not warriors in the traditional sense, but their laboratories were battlefields of precision, where every equation was a weapon and every experiment carried mortal weight. Unlike German scientists, who worked under the rigid command of the Reich's military hierarchy, American researchers enjoyed collaboration and freedom to innovate. That culture, open, interdisciplinary, and fast-moving, became America's real secret weapon. They could borrow an idea from radiophysics one day, apply it to bomb fuses the next, and see it mass-produced within weeks. It was industrial creativity at wartime speed, and that, more than any single device, was what Germany could not match. Magnetic weapons demanded precision unlike anything conventional manufacturing had ever produced. A single misaligned coil or miscalibrated amplifier could render the entire fuse useless. To meet these standards, America mobilized its civilian industries with military precision. Factories that once built radios or household appliances were transformed overnight into assembly lines for magnetic ordnance. Women trained in electrical assembly wound thousands of copper coils, each thinner than a thread of hair. Their work required absolute accuracy, because one bad solder joint could mean a bomb that failed, or worse, detonated prematurely. By mid-1944, more than 2,000 industrial plants across the U.S. were producing components for influence fuses. The scale was staggering. Each month, American factories turned out tens of thousands of magnetic bombs, torpedo triggers, and aerial mines, more than the entire annual output of Germany's precision munitions industry. But what made this effort extraordinary was not just quantity. It was reliability. Every fuse was tested against controlled magnetic fields before shipment. Each one was a product of physics, engineering, and faith. Faith that invisible forces could be controlled and weaponized. When fragments of magnetic bombs reached German laboratories in late 1944, the reaction bordered on disbelief. At the Reich Institute for Materials Research, engineers tested captured fuses from Allied mines dropped along the Baltic coast. They dissected the components, vacuum tubes, sensors, and glass-sealed amplifiers, and found no moving parts. No pressure plate, no mechanical trigger, just silent magnetism, waiting to react. Reports sent to Berlin described them as electromagnetically reactive ordnance of unorthodox construction. The scientists concluded that the Americans had achieved something unprecedented, the first truly intelligent detonation mechanism. They called it unheimlich, uncanny, because in it they saw not just a new weapon, but a new age, one in which the laws of physics themselves could be commanded to fight. And that realization would soon reach the battlefield. As Allied bombers took to the skies over Europe, those same invisible sensors began rewriting the physics of destruction. Bombs no longer needed precision, only proximity, and every piece of metal below became a potential target. War has always carried terror, but invisible weapons introduce a new kind of dread. When explosions come without contact, sailors and civilians feel cheated by reality itself. Japanese and German reports from 1944-45 read like the journals of men haunted. Captains' logs recorded ships blown apart in calm seas. Port workers wrote of piers shuddering without any enemy plane overhead. The unpredictability was corrosive. It wore down confidence. A seaman who survived a magnetic blast would never forget the silence before the shock. There was no roar, one survivor later recalled in an oral history. Just a stillness. Then the world folded. That stillness is the true weapon of influence ordnance, It turns the environment into an adversary. Convoys that once trusted charts and sweepers began to doubt every crossing. Commanders delayed sailings. Supplies slowed. Schedules broke. In cities, repeated unexplained detonations lowered morale. Factories guarded their concrete and steel like sacred things. Yet concrete shields meant little when the blast came from a field. The constant threat reshaped civilian life. Night watchmen stayed at posts longer. Harbor pilots learned new rituals of caution. Fear became an operational factor, not merely a human one. For Allied planners, this was deliberate. The goal of magnetic mines and influence bombs was not only to destroy tonnage, but to sap the enemy's will to move. A port that cannot be trusted is a dead port. A rail line whose bridges might collapse at any moment is paralyzed. The weapon worked as much on mines as on metal. If war is logistics, then influence ordnance attacked its arteries. Magnetic mines were never merely tactical devices. They were strategic instruments. Operation Starvation, the U.S. aerial mining campaign against Japan in 1945, exemplified that logic. B-29s, flying from the Marianas, scattered naval mines into choke points, estuaries, and harbor approaches. Many of those mines used magnetic or combined influence fuses intended to detonate in proximity to ship hulls. The result was dramatic. Japanese merchant shipping was crippled. Fuel and food supplies dwindled. Ports ceased to function normally. Strategists in Washington and in Allied theaters saw the consequence immediately. You did not need to sink every freighter. You only needed to render sea lanes unreliable. A few well-placed magnetic minefields could halt entire fleets of merchantmen, redirect convoys along longer, more dangerous routes, and force constant minesweeper patrols that bled resources. The Allies used that leverage thoughtfully. They synchronized mining with blockades, air raids, and submarine patrols to multiply effect. Magnetically triggered devices became part of a larger ecosystem of pressure, one that finally strangled the logistical lifelines Germany and Japan depended upon. New weapons always provoke ethical debate. Magnetic ordnance raised questions then that echo still today. The devices were blunt instruments. They could not discriminate between military and civilian tonnage if both carried metal. A hospital ship stripped of armament but built of steel remained vulnerable. A supply train with essential foodstuffs could trigger the same effect as an armored convoy. Allied planners argued the point with the bluntness of total war. If blocking enemy supply lines shortened the conflict and saved lives overall, the collateral suffering was a necessary cost. Commanders in the Pacific framed aerial mining as humane. Fewer face-to-face battles, fewer mass urban bombings. Yet for those on the receiving end, the suffering was immediate and real. After the war, captured German reports catalogued such moral ambiguity. Port administrators described how magnetic mines had turned neutral merchantmen into accidental casualties. Local populations faced starvation not only from direct bombardment, but from the invisible choke of mined approaches. The ethical ledger of influence ordnance would become part of post-war questions about conduct in total war. Perhaps the most important Allied insight was that technology could force the enemy to adapt, and that adaptation could be exploited. When Germany and Japan scrambled to counter magnetic fuses, they diverted men, factories, and materials. Degaussing programs expanded. Minesweepers multiplied. Ports invested in new infrastructure and redundant routes. Every countermeasure was itself a resource drain. The Allies counted on that redistribution. By making the enemy fight for safety, they gained initiative elsewhere. Aircraft could be redirected to softer targets. Submarines could exploit the gaps. Land offensives found fewer supplies moved to the front. This logic was not purely destructive. It was strategic economics. Influence ordnance functioned as a force multiplier that amplified Allied power without requiring equal numbers of attacking ships or planes. By late 1944 and into 1945, German engineering reports reveal a cold, begrudging admiration. Fragments sent to Kiel and Berlin showed components that were elegant and compact. Induction coils, vacuum tube amplifiers, and carefully calibrated relays. Interrogations of captured Allied technicians disclosed organized manufacturing and testing programs. One internal German memo, later translated after the war, observed, "The enemy weaponizes the invisible. We fought the visible and now face systems that punish our doctrine." That admission marks the turning point in their understanding. Not merely that a new device existed, but that a whole new logic of warfare had arrived. It was a logic built not on the mass of steel thrown into battle, but on the way fields and signatures could be measured and prosecuted. And this logic would soon be tested in the war's decisive campaigns. When Allied fleets and air armadas carried magnetic ordnance into battle, the effects were not only physical destruction, they were strategic ruptures, moments when the enemy's plans met an opponent who had learned to fight the invisible. That realization leads directly to the moments when these weapons were used at scale, the bombs and mines that stunned harbors, split convoys, and left German engineers scrambling for answers. The Luftwaffe spotters on the cliffs watched American bombers pass overhead, silver arrows glinting in the sunlight. They braced for the familiar thunder of impact. Instead, the bombs vanished into the water beyond the docks. Seconds passed, then the sea erupted. Walls of spray leapt 50 feet high, ships twisted at their moorings, and concrete quays fractured as if struck from beneath. Nothing had touched them. Divers sent into the wreckage later found no direct hits. Hull plates were peeled outward, bulkheads buckled, and cranes overturned by shock waves that began below the seabed. The conclusion was inescapable. The Americans were using a weapon that detonated not on contact, but in response to the metal itself. Within days, identical reports arrived from Cherbourg, Saint-Nazaire, and Kiel. German engineers confronted a pattern they could not explain. Bombs falling short still killed. Torpedoes exploding meters away still split hulls open. They soon learned the name whispered among Allied aircrews: magnetic influence bombs. The secret lay inside a fuse no bigger than a wristwatch. Coils wound around soft iron cores detected the distortion a ship or submarine made in Earth's magnetic field. When that disturbance matched a precise amplitude, a relay closed the circuit. The detonation was instantaneous, mathematically perfect. To the Kriegsmarine, this was nightmare physics. No armor could protect against a field. Degaussing might shield a vessel from mines, but not from bombs dropped from the sky. The very metal that gave a warship its strength had become the source of its vulnerability. At Brest, Admiral Dönitz ordered urgent counter-analysis. Laboratories at Kiel and Peenemünde dissected fragments of unexploded ordnance retrieved from mud and tide. What they found left them speechless. Miniature vacuum tubes sealed in resin, glass capacitors the size of thimbles, and a battery system that stayed active for hours after release. The circuit responded to gradients so subtle they could only be measured with laboratory magnetometers. One report concluded bitterly, "The enemy has combined electronic sensitivity with ordnance efficiency in a manner not yet achievable in the Reich." The shock was not only technical, but philosophical. For years, German design had pursued mechanical perfection: stronger armor, higher velocity, precise machining. The Americans had pursued something intangible: fields and signals. They had turned the unseen into a trigger. In the following weeks, Allied bombers exploited the new weapon relentlessly. U-boat pens, once considered invulnerable, massive concrete cathedrals of war, shuddered under internal pressure waves. The magnetic bombs didn't need to pierce the roofs. They detonated near the steel reinforcements, transmitting vibration that rippled through the structure like a bell. At Lorient and Hamburg, entire docking bays collapsed inward. German intelligence at first suspected sabotage or secret British tunneling charges, but captured fragments told the truth. What terrified them most was the consistency. Every explosion occurred within the optimal magnetic range. No premature or delayed blasts. Precision had reached a new form: field accuracy. In Washington, scientists read decrypted Enigma traffic describing the confusion with quiet satisfaction. Their creation had crossed the threshold from experiment to doctrine. The Office of Scientific Research and Development logged the campaign's success under a modest heading: Applied Magnetic Ordnance, Europe Theater. Behind that sterile phrase lay one of the most decisive demonstrations of American scientific warfare. Even German pilots noticed the change. During raids on supply ports, they reported anti-aircraft guns that misfired after shock waves distorted their mounts, cranes that collapsed, though no shell struck them, and ships torn apart by invisible pressure. To the men on the ground, the enemy had learned to weaponize the planet itself. The impact reached beyond the battlefield. At universities across Germany, physicists were summoned to consult on magnetic shielding, but the resources simply weren't there. Copper was rationed. Laboratories lacked precision instruments. Every day lost meant another harbor crippled. Dönitz ordered U-boats to disperse to less exposed bases, a desperate measure that only complicated logistics further. By August 1944, the Allies had effectively neutralized Germany's western naval infrastructure. Brest fell, and with it, one of the Kriegsmarine's last major repair hubs. Analysts later estimated that magnetic bombs and mines accounted for nearly a third of the harbor's destruction. The rest came from conventional explosives. But it was the mystery of the magnetic weapons that broke morale. A captured German engineer later confessed, "We could explain every explosion except those." When steel itself became the target, we realized the war had moved beyond engineering. He was right. The magnetic bomb marked the frontier between mechanical war and electronic war, a boundary that Germany, for all its brilliance, could not cross in time. And as winter closed over the shattered docks of northern Europe, the Americans prepared to deploy the same principle in an even deadlier form beneath the waves and across the Pacific. Pacific Ocean, January 1945. Night fell like ink over the Philippine Sea. A Japanese convoy crept southward under blackout. Tankers, troop transports, and escorts. The water was calm, radar quiet, and no aircraft appeared on the horizon. Then the sea itself exploded. A wall of fire lifted from beneath the lead tanker, rolling oil and steel into one molten column. Moments later, another detonation split the formation. No torpedo tracks, no wake, only invisible forces rising from the deep. The bombs had been dropped hours earlier by B-29s hundreds of miles away. They were magnetic naval mines, each armed with the same principle that had stunned German engineers months before. They didn't need contact. They only needed to sense the metal above them, the faint distortion a ship's hull made in the planet's field. And they were devastating. Operation Starvation, led by the U.S. Army Air Forces under Admiral Chester Nimitz's strategic direction, scattered nearly 12,000 such mines across Japan's harbors and inland sea routes in 1945. Most carried combined magnetic and acoustic triggers, the pinnacle of Allied ordnance science. Within weeks, Japan's maritime lifelines collapsed. The once busy inland sea turned into a floating graveyard of rusted hulls and broken bridges. Merchant shipping losses skyrocketed. Coal from Kyushu never reached Tokyo. Food supplies rotted in coastal warehouses. By spring, more than 80% of Japan's remaining merchant fleet lay sunk or stranded. And what terrified the Imperial Navy most, they could neither see nor disarm the mines fast enough. Japanese engineers, like their German counterparts, dissected recovered fuses in disbelief. They found not explosives first, but electromagnetic logic. Coils, resistors, and capacitors precisely calibrated to trigger when magnetic flux changed in a specific curve. The fuses even included self-neutralizing timers, designed to deactivate after a set number of days, making them nearly impossible to study before they expired. Reports from Tokyo's Naval Technical Research Institute admitted the grim truth. Enemy mines exhibit intelligence beyond our current electronic capacity. The word intelligence was not metaphor. For the first time, weapons responded to the world they perceived. That was the true revolution. Meanwhile, in Europe, Germany was collapsing. By February 1945, Allied advances had cut off many of the Reich's research centers. Yet the remnants of its scientific community kept analyzing captured ordnance. At Peenemünde and Kiel, fragments from both aerial bombs and naval mines were logged under Beutegeräte, captured devices. One report detailed the internal geometry of a U.S. Navy magnetic mine. Sensor tuned to the declination of Earth's field. Contains glass-encased amplifiers of exceptional miniaturization. Circuit complexity surpasses domestic design by factor 4. The Germans understood the principle. They had pioneered similar fuses for mines in 1939, but theirs were large, temperamental, and unreliable. They lacked the industrial finesse to make them stable under flight shock or underwater pressure. America, with its massive manufacturing base, had perfected what Germany had only theorized. That realization hit like defeat itself. The Reich had invented the magnetic mine in 1939 to terrorize British shipping, and Britain's scientists, led by the Royal Navy's mine section, had reversed it within weeks. But now, 6 years later, Germany faced the perfected version of its own creation. The technological circle had closed, and America had finished the equation. Admiral Karl Dönitz later admitted, during post-war interrogations, that magnetic bombs neutralized the advantage of concrete. The U-boat pens at Lorient, Saint-Nazaire, and Wilhelmshaven, once thought impregnable, were rendered unusable not by direct hits, but by field shockwaves. Each blast warped cranes, collapsed doors, and severed dry dock pumps. The Germans had built fortresses for a mechanical war. The Allies had brought an invisible one. At Peenemünde, a final desperate project tried to copy the American fuse. Engineers from IG Farben and Siemens were ordered to replicate the U.S. induction circuits using salvaged copper and glass. They succeeded, partially. Their model worked in laboratory tests but failed in the field, unable to resist vibration and temperature fluctuations. Without industrial stability, precision meant nothing. The war had moved too fast. A young physicist in one report wrote bitterly, "They have married physics and production. We have only the theory." That sentence summarized Germany's downfall. Its scientists still knew how to innovate, but they could no longer manufacture the future. In the Pacific, the consequences were total. By late March 1945, Japanese shipping losses reached catastrophic levels. Oil imports from the Dutch East Indies stopped completely. Fishermen refused to sail. Even the Imperial Navy's largest battleship, Yamato, sailed to Okinawa in April without adequate escort because every available vessel had been crippled or destroyed, many by magnetic mines. At sea, Japan was suffocating in silence. The Americans didn't need to fight every ship. They just let the magnetic fields do the work. And that was the ultimate strategic lesson. Invisible power wins wars of exhaustion. While the German engineers tried in vain to replicate the technology, and Japanese divers risked their lives sweeping magnetic sensors with bamboo poles, America had already moved on, combining magnetism with proximity radar and electronic fusing for the next era of ordnance. From the air to the sea, the principle was the same. a bomb that knew its target, a weapon that didn't guess but detected. It was the first whisper of modern smart weaponry, born from coils of copper and the steady hum of the planet itself. By the war's final months, captured German scientists finally understood what they were facing. Their laboratories had produced rockets that reached the edge of space, but their enemies had learned to weaponize invisible forces that surrounded every inch of Earth. When Allied troops entered Kiel in May 1945, they found crates of half-assembled magnetic countermeasures and folders labeled magnetische Entzerrung, Gegenwaffen. But there were no working prototypes, only diagrams, the ghost of an idea. One British officer examining the files wrote in his report, "They sought to master the magnet, but the magnet had already chosen its side." The field had turned, literally and symbolically, against them. And as the war ended, the silent weapon that had begun in secret American laboratories would become the blueprint for decades of guided warfare to come. May 1945. Germany surrenders. The war that began with steel and fire ends with circuitry and silence. All across the Reich, Allied scientific teams move through the wreckage of a nation that once led the world in engineering. They're not looking for tanks or rockets now. They're looking for ideas. At the naval testing grounds in Kiel, British and American officers sift through abandoned research logs. Between half-burned blueprints and rusted metal fragments, they find meticulous notes written in the margins of engineering reports, calculations of magnetic flux, sketches of field sensors, prototype circuits. Each one is an echo of Germany's frantic attempt to catch up. But they are too late. The American magnetic bomb had already rewritten the laws of naval warfare. The Allies quickly understood what they had accomplished. For the first time in history, a weapon had not relied on direct impact, line of sight, or even human judgment. It relied on the environment itself. The sea, the air, the planet's magnetic field, all had become part of the trigger mechanism. In that realization lay the foundation of post-war defense research. From Washington to London, the lessons were immediate. If magnetism could destroy ships, what else could fields control? The same laboratories that designed influence bombs were soon experimenting with radar-guided shells, proximity fuses, and early guidance systems for rockets. What had begun as a wartime necessity was becoming a peacetime revolution. The birth of electronic warfare. Meanwhile, in Germany, scientists who once designed magnetic mines now found themselves working under new flags. Through Operation Paperclip, many were brought to the United States. Others went to the Soviet Union, absorbed into competing programs. Their knowledge of magnetic sensing, detonation physics, and field theory fed directly into Cold War weapons design. Ironically, men who had studied how to defend against magnetic bombs were now helping their former enemies refine them. At Fort Monmouth and Dahlgren, captured German documents were translated and catalogued. American researchers discovered that by 1944, German laboratories had already explored hybrid, acoustic magnetic triggers and magnetic torpedo guidance concepts that would soon reappear in post-war submarine technology. What Germany lacked wasn't intelligence. It was time, resources, and freedom. Its science had been caged inside ideology. America's had been unleashed by collaboration, and in that difference lay the true victory. By late 1946, reports from the U.S. Navy's Bureau of Ordnance openly credited wartime magnetic research as the most significant advance in underwater weaponry since the invention of the torpedo. Experiments at the Naval Research Laboratory continued under a new title, Magnetic Anomaly Detection, AAD. Originally developed to find submarines, it used the same principles as the bombs that had shocked German engineers, sensing distortions in the Earth's field to reveal what could not be seen. The technology soon evolved beyond warfare. Aviation engineers adopted magnetic detection for navigation and survey mapping. Geophysicists used it to locate mineral deposits. In a paradox of history, a weapon of destruction had become a tool of discovery. In Europe, the psychological wounds ran deeper. German naval officers, once proud of their engineering supremacy, struggled to comprehend their defeat, not by numbers, but by science itself. Their post-war testimonies often return to a single phrase: they fought with mathematics. We fought with machinery. That sentence echoed through debriefings and military journals alike. It marked a shift in philosophy, a recognition that mastery of raw materials was no longer enough. Victory now required mastery of the invisible. The same realization dawned in Japan. When Allied inspectors visited Yokosuka Naval Arsenal after surrender, they found hundreds of incomplete diagrams attempting to reproduce Allied magnetic mines. The Japanese had understood their purpose, but not their construction. Without access to high-precision components, they could only guess at the circuitry. Their engineers recorded, with reluctant admiration, that the enemy's weapons appear to function by unseen law. That unseen law, the harnessing of magnetic and electronic fields, would define every major military technology of the 20th century: radar, missiles, sonar, nuclear triggers. All grew from the same roots planted in secret wartime laboratories where scientists first asked, "Can we make a bomb that senses its target?" By 1947, the world's militaries knew the answer: yes, and now they wanted more. 1947. The new war begins in silence. The laboratories that once built magnetic bombs for B-29s now hum with new ambitions. Their doors bear new names: Guidance Division, Electronic Warfare Department, Weapons Analysis Section. But the mission remains the same: control the invisible. From Washington to Moscow, the magnetic principle becomes doctrine. The same physics that sensed a ship's hull beneath the sea now guides missiles through the air. In the United States, the Office of Naval Research and the newly formed Air Force begin integrating magnetic sensors into anti-submarine aircraft and early guided munitions. In the Soviet Union, teams of captured German physicists rebuild magnetic influence mines for coastal defense and experiment with fuses for atomic delivery systems. The age of magnetism has turned into the age of electronics. The weapon that began as a coil of copper wire has now rewritten strategy. Before the magnetic bomb, naval warfare was about armor and tonnage. After it, survival depended on signatures. Every vessel now carried its own magnetic fingerprint, an invisible calling card detectable by machines. This realization changed the way nations built fleets. By the 1950s, new ships were designed with non-ferromagnetic alloys and fitted with degaussing systems, networks of cables that counteracted their own magnetic fields. Naval architects no longer asked how thick armor should be, but how quiet a ship could become to a magnet. Submarines evolved from predators to phantoms, their steel skins layered with special materials to disguise them from detection. It was a paradox. The more advanced the science, the less visible war became. Conflict retreated into wavelengths, flux patterns, and invisible geometry. The industries born from magnetic ordnance never closed their doors after 1945. DuPont, General Electric, RCA, and Bell Laboratories redirected wartime funding into peacetime electronics, sonar systems, television, and early computers. The proximity fuses and magnetic sensors once hidden inside bombs became the ancestors of transistor logic. In 1953, a Bell Labs engineer noted, almost casually, that the same magnetic amplifiers used in influence mines could stabilize data pulses in a new computing device. He was right. The logic of destruction had become the logic of information. America's wartime factories, the same assembly lines where women had wound copper coils for bombs, now produced circuitry for radios, aircraft, and eventually satellites. The invisible weapon had become the architecture of modern life. Yet even as prosperity returned, a quiet unease spread among those who had created the technology. Men like Dr. Merle Tuve, who had once overseen magnetic fuse research, spoke of his discomfort in later interviews. He said, "We learned that every discovery has two futures, the one we hope for, and the one the world chooses." That sentence became a kind of confession for the scientific generation that had armed democracy with fields and circuits. They had saved lives by shortening the war, but they had also opened a door that could never again be closed. The same understanding haunted their former German counterparts. Many who joined American or Soviet projects under new flags saw their wartime inventions reborn in the arms race they had hoped would never come. Where once they measured ship signatures, they now calculated magnetic shielding for atomic bombs and missile guidance. The science had no allegiance anymore. It belonged to whoever could build faster. When military historians later described the Second World War, they divided it into two eras: the mechanical war, of tanks, shells, and engines, and the electronic war, of radar, radio, and the magnetic fuse. The line between them was drawn not on a battlefield, but in a laboratory. The day a weapon sensed its environment, the human hand ceased to be its only guide. It was the quiet beginning of automation, the idea that machines could make decisions once reserved for men. From that point on, every generation of weapon would carry a trace of that same DNA. Heat-seeking missiles, smart bombs, drone sensors, all were descendants of the magnetic mind that first learned to feel the world. And though the men who built it never intended to create a philosophy, they did. They proved that intelligence, even in its simplest mechanical form, could be engineered. That realization would ripple beyond warfare, shaping the birth of computers, robotics, and the digital age itself. By the 1960s, few remembered the original magnetic bomb. It had become an artifact, a piece of circuitry in a museum case. But its principle endured everywhere, silently running beneath the surface of modern civilization. Every time a pilot armed a guided bomb, every time a satellite corrected its orbit using magnetic sensors, it traced its lineage back to 1944, to the shattered docks of Brest, to the stunned engineers who stared at a weapon that could sense them before they saw it. The war was long over, but its fields still hummed beneath the earth. In the quiet decades that followed the war, the oceans forgot their minds. Waves rolled over wrecks, salt corroded metal, and the magnetic fields that once sensed death returned to silence. But the legacy of those weapons never faded, because their true battlefield was never the sea. It was the human mind. When German engineers first examined a magnetic bomb, they thought they were seeing a miracle of engineering. In truth, they were witnessing a shift in civilization. For the first time, man had built a weapon that felt. It did not see its target or strike by contact. It recognized a change in nature itself and acted upon it. That was no longer the age of machines. It was the beginning of the age of perception. From that moment, the essence of warfare changed. Strength no longer meant thicker armor or heavier guns. It meant the ability to understand what could not be seen. The scientists who built these fuses and sensors didn't merely design new weapons. They redefined intelligence as something that could be manufactured, repeated, and mass-produced. And in doing so, they blurred the oldest boundary in history, the line between human judgment and mechanical reaction. Every smart missile, every guided drone, every sensor that knows what it's looking at owes its ancestry to those coils of copper and glass born in 1944. But beyond the technology lies something deeper, a lesson that every great power has had to relearn since, that the mastery of nature's invisible forces brings not only strength, but reflection. Because every new layer of control over the world demands a new measure of control over ourselves. The magnetic bomb was not the loudest weapon of the Second World War, nor the deadliest. It was the quietest, and perhaps the most prophetic. It whispered of a future where victory would depend not on what could be forged, but on what could be imagined. In that sense, it marked the true turning point of modern history. A war fought with iron had ended, and a new one, fought with ideas, electrons, and invisible fields, had just begun.